Hi, my name is Zachary Henning. I'm a student at University of California, Berkeley, and this is my term project for Bioengineering 147, and it is titled Modeling a Metabolically Engineered Strain of E. coli to Produce 2,3-Butane-Diol in Aerobic Conditions. Now, metabolic engineering is of great importance to society because it has implications to both the economy, as it being cheaper to produce than some chemical and industrial means, as well as the environment, because a lot of industrial products are derived from petroleum and fossil fuels. So the faster that we can move away from that, the faster we could, um, end our dependency on fossil fuels. So I decided to look at 2,3-butane diol synthesis, and this is primarily because it's a high-value chemical in the pharmaceutical industry, as well as plastic polymer production, as well as other industrial polymer productions. I decided to use glycerol as the main carbon source, and this is mainly due to research by Raman et al. That shows this new enzyme, DHAD, increasing the rate of glycerol uptake into the central metabolism. And as you can see here, here's a quick overview where we have glycerol coming down to pyruvate, then ethanol acetate, 2,3-butane-diol, lactate, and to the citric acid cycle. Now, recent research has also shown that in the presence of high oxygen, 2,3-butane-diol synthesis tends to get pretty low, and that's mainly probably due to the fact that high oxygen takes pyruvate and pulls it heavily towards the citric acid cycle, and so the cell could do biosynthesis, grow, divide, etc. So I propose that butane diol synthesis happen in these bacterial microcompartments in which we could draw pyruvate and NADH into the system to perform the final reactions from pyruvate to acetolactate to acetone, finally to 2,3-butane-diol, undisturbed and unperturbed within the bacterial microcompartment. This way, there's no back reactions of the pyruvate or pyruvate constantly going to the TCA instead of into the acetolactase acetone 2,3-butane-diol synthesis pathway. So here is the basic design of my genetic circuit. So draw your attention here. Here's a quick overview of it where we have two inputs, IPTG and ATC. ATC activates the ARC-A operon, and the ARC-A operon, which contains LAC-I, will go on to repress all subsequent operons. Now we have the DHAD operon also repressing the TET-R promoter through the TET-R protein, and that can be induced by ATC. So what we basically have here is a Collins-Gardner style toggle switch, but instead of using heat as one of the factors, I decided to just use TET-R and LAC-I. And as you can see, the activation of the PLAC-I promoter, or the lack of LAC-I, produces DHAD, tail1, and TET-R. So TET-R goes on to repress LAC-I, allowing for these to be expressed, but these also need activators. So tail1 activates the PLAC-I tail1 promoter, and that transcribes the enzymes that need to be packaged within the bacterial microcompartment, as well as a second activator, which activates the actual proteins that make the bacterial microcompartment. Now here's the basic logic design of the circuit. Over here we have the basic toggle switch, the two OR gates with one inverter on each input. So we have one input of ATC, one input of IPTG, and then if this is on, it'll go on and activate this AND gate with this being off because we have this inverter. So this gets activated and goes on and gives one input here, and then if this is deactivated, then this will go on and give a 0, which is inverted to a 1 input here, leading to BMC butane-diol synthesis. Alright, now the first thing to examine was the dynamics of the toggle switch. I wanted to see how TET-R and how LAC-I would behave together. And as you can see from this graph right here, they behave pretty well. Not a very long time for the states to change. Right here, we would be putting in ATC, relieving TET-R, and allowing for the transcription of LAC-I and the shutting off of the system. And then here we would have the addition of IPTG, allowing for the transcription and repression properties of TET-R to be expressed. And over here we see some slight differences. We see that TET-R is pretty responsive to ATC, just a little bit of ATC, and we have an increase of the ARC-A operon. And then over here we have some slightly slower dynamics with IPTG and LAC-I. As we see, we need just a tad more IPTG added to the system in order for DHAD operon expression to be maximized up here on the plane. Now for the Cascade Dynamics, first let's look at this figure B here. So what we see here is the first and second operons. The operons involved in the toggle switch are both being transcribed. This is a system without IPTG or ATC. This is just the initialization I wanted to look at and see how this unfolds. As you can see here, because these mRNA levels are getting up, there is some translation happening, which is subsequently repressing the levels of the BUD operon and the BMC operon here. As you can see, it maxes out around 6 for both on average, maybe slightly a bit above 6. It's because LAC-I is being translated enough to begin repression of these operons. Now, if we start the system with IPTG here, we see a higher output of mRNA. And as you can see here, there is little to no just basal transcription of the mRNA operon, and it doesn't seem to really affect the transcription of the other operons and the creation of their mRNAs, because we actually have higher outputs for all of them compared to when we initialize the system without IPTG. So one thing I wanted to look at was the effect oxygen has in the system, and as previously mentioned, it's probably due to the fact that pyruvate is constantly being drawn off into the biosynthesis pathways of the citric acid cycle, etc. So as we can see here, without BMC, we have some pretty low transcription and synthesis levels of BTD, butanediol, and higher levels of acetyl-CoA. I just used acetyl-CoA as a marker for pyruvate going into the TCA cycle. Now, with the addition of BMCs, what we see here actually is a drastic increase of titer levels of BTD. This is over the course of 10 hours. I'm going to use nanomole here just as an arbitrary unit with rate. And what we see here is about 60% increase of BTD throughout the system, which is pretty great if you look at it. And this is probably due to the fact that pyruvate is constantly being drawn off into the BMCs, so the central metabolism is replacing it to send pyruvate into the citric acid cycle. We also see a lower level of acetyl-CoA being synthesized here. Now, one thing I wanted to look at because of those results was the changing of diffusion into the BMC. And as expected, increasing the diffusion rate drastically increases the rate of butanediol synthesis. As you can see here, butanediol synthesis is drastically increasing, close to 40 or 30%, I would say, increase in butanediol synthesis. So this would require some protein interaction dynamics to change because the BMC uses the one of its shell proteins to actually pull things in. It is not natural diffusion throughout the environment because the BMC is actually not that porous. It's pretty selective on what it lets in. So future directions with those results is To analyze the addition of an extra layer of LAC-I into R, just maybe see if we could get that lag due to that mRNA-2 operon synthesis to go away. Definitely increase the rate of diffusion into bacterial macrocompartments in the real world and see what we could achieve, how long it would take to do that, and increase butane diol synthesis in a population. Next, actually study the population production in a bioreactor. Basically expand the scope to an entire population and see the diffusion rate of IPTG in a bioreactor or ATC in a bioreactor and see the results. Finally, we need to collect biochemical data. I think this is the most important thing. We need empirical results. We need empirical data to either collaborate with the model or to allow us to reassess the model, and that's going to require a lot of wet lab work. All right, thank you very much.